In this lecture, we study the voltage regulator. So we are using Zener as a voltage regulator. So what is the definition of voltage regulator? Output voltage should maintain constant when if the input voltage fluctuates or output load varies. In both the cases, output should not vary. That is called the voltage regulation. Here, this is the characteristics. If you see, we use this Zener in a reverse bias, that too in the breakdown region. Now, in this region, we use Zener as a voltage regulator. And if you see here, voltage is a constant and current is changing, current is increasing. So this is the region called the breakdown region. We use Zener in this region. So here Zener is connected, negative, already I said that in a reverse bias. So positive plate of the supply is given to the negative material of the diode. So in a reverse bias, Zener is connected and load is connected in parallel with the diode, so that when Zener gets breakdown, Zener across the Zener, the voltage is fixed. The same voltage will be available across the load. So in a parallel, voltages are same. That's why the same Zener voltage will be available at the load or at the output. Now, if you take these two terminal, this is a resistor, and this voltage we can also call it as a VL. VL or V naught, both are what? It is nothing but a VZ only. Why? Because these two are connected in parallel. Whatever the VZ Zener voltage is there, the same voltage will be available at the load. When it will be available, here you can see the current flowing through the Zener is IZ minimum, then only it is giving the breakdown. If current flowing through the Zener is less than this IZ minimum, then here you can see the voltage is not a VZ voltage. Here it is 0. As the voltage is increasing, across the Zener also voltage is increasing. And after reaching the VZ, Zener breakdown only, so it is giving the constant voltage and current is increasing. So below the IZ minimum current, Zener will not give the regulation. That's why what? We have to design the circuit such that here the current should not go below the IZ minimum value. And also here if you see IZ maximum, and if the current flowing through the diode is increases to the beyond the IZ maximum, then the power dissipation here it is increases, thereby Zener gets heat and Zener gets damage. That's why we should not allow the excess current. We have to allow the current through the Zener within these limits to achieve the regulation. Here this current limit is what? IZ minimum to the IZ maximum. Within this limit only, we have to allow the current flowing through the Zener. Then only it will give the regulation. So to get this, now we need to calculate the, now this is the supply. And here the current which is flowing in this resistor is, we need to calculate the RS resistor. We connected one series resistor. We need to calculate the RS resistor such that the current flowing through the IZ Zener should be within this range. Now, if current flowing through the RS is IS and the voltage across the RS is VS, then how to now here this is the node and this current is IZ current and this current is IL current. Now this current is what? IZ current. This is the range. Okay, this is the range. This is IZ current. So now apply the KCL at this node. Then IS is equal to IZ plus IL. Entering currents is equal to leaving currents. So now here RS is equal to, how can we, now after knowing the IS, and if we know the V in, and if you know the diode breakdown voltage, when you are picking this diode, you know the diode breakdown voltage, then we can find out the RS. So RS, how can we find out? RS is nothing but what? VS divided by the IS. Then how to calculate the VS? It is nothing but a potential difference of V in and VZ. Then how to take the formula potential difference? This is V in minus VZ divided by IS. Then why I have taken V in minus VZ? Why not VZ minus V in? Means see the current direction. Now current is coming from the V in. So that's why we have to take the V in minus VZ. Now this is a formula for the RS. Now here VZ, here diode and load both are connected in parallel. That's why here VZ is equal to VL. Or if you are, we wanted to represent this as the output voltage, you can also call it as a V naught. So these are the, now like this, we have to design the RS value for the regulator. Now here in a voltage regulator, there are two types of regulations are there. One is a line regulation and another one is a load regulation. Line regulation means what? By varying the line and keeping the load, how the diode is maintains the gives the regulation that we will analyze under the line regulation. Here line we are varying and load we are keeping fixed. So with this what happens, if the input is varying, then the IS varies. Then IS is equal to what? IZ plus IL. If input is increased, then what happens? IS increases. Thereby, now here we are not changing the load. So IL is not going to change. What happens to the IZ? Excess current is drawn through the, now Zener will draw the excess current. Now if the IS is reduced, then IL is constant over here. Now load is fixed. So through the load, fixed current is going to flow. So the if input current is reduced means what? Current flowing through the Zener reduces. And we have to see that this when the current is reducing, this should not go beyond IZ minimum. And when the current is Zener current is increasing, means this should not go beyond the below the now here the IZ current should not go below the IZ minimum, and maximum current should not go beyond the IZ maximum. So thereby what? It Zener maintains the output voltage constant. If any excess current is coming, that is drawn by the Zener. So like that, it is keeping the output current constant. So output voltage also maintains constant. So here you can see the line regulation characteristics. This is a 0 volt. Line regulation characteristics are taken between Vs and V naught. So input supply and in output voltage. For these two characteristics are drawn. As the input voltage is increased, so output is also changing linearly. Output is also varying linearly. And once the breakdown voltage occurs, now here, once the breakdown voltage occurs, then the output voltage maintain constant. Meaning is what? Here, if you are keeping 0, means what? That time what? Now, if you see the characteristics of the Zener, at the 0, it is 0. Across the Zener also 0 only. As you go on increasing the input voltage, so when it reaches to the Zener voltage, then only it is maintaining the constant voltage. Otherwise, linearly the Zener voltage also varying. That's why output voltage also varies linearly. Once the breakdown occurs, if the input voltage is more than the breakdown voltage, then the output is a constant. Now this is for ideal case and this is for the practical case. Practical case is nothing but what? The resistor drop we have to consider. Now for example, if I wanted output voltage as a 5 volts fixed, then I have to pick the 5 volts Zener breakdown. Now the Zener which is having the 5 volts Zener breakdown. And input I have to give. Now here I have to calculate the resistor such that here, if I know the IS value, if I know the RS value, how much the voltage drop I have to calculate. Accordingly, I have to fix the V in value. Now, mostly if I take the 5 volts, I won't get the 5 volts at this point because some drop is at the RS. So that's why I have to give always more than the Zener voltage at the input. Then only I will achieve the regulation at the output. This is about the line regulation. Now coming to the load regulation, here need to keep the input voltage fixed and vary the load. Now, if load is varied, but input voltage is fixed, at the time, how the Zener maintains the regulation. So for that, what IS is equal to again what? IZ plus IL. Now here IS is constant. Voltage is not going to change. So that's why IS is also not going to vary. So IZ plus IL. So if IL is increases, then IZ value decreases. Why? Because if more current is drawn by the load, then the Zener will take the less current. If the less current is drawn by the load, then the remaining excess current is drawn by the Zener. Here, if the load current is reduced, then the Zener current increases. Means what? Zener draws the more current. Like that, so it will maintain the output voltage constant. So this is about the load regulation. Now, if you see the characteristics, so it is IL, load current versus output voltage. As the load current is increasing, now this is the ideal case. For all the load current values, the output voltage should maintain constant. But as the load current increases, then now here we will take like this. Load current increases, then the regulation, it will not maintain regulation. Why? Because if load current is increasing means what? IZ current is reduced. If the IZ current is reduced, now if this current is below the IZ minimum, then it will not give the regulation. Now this is the VZ. If this is the I minimum value or I knee value, I knee value. If it is below this current, then it will not give any regulation. So that's why as the current, load current increases, so Zener gives the poor regulation. Now this is about the Zener as a voltage regulator.